Assalamualaikum and hello. So today I would like to give a lecture on kinematics of fluid motion. So this is in lecture 4. So the contents of this lecture are given on the slide. So basically these are all the terms and also concepts that you need to remember and understand, of course, because you will use this when you analyze the fluid motion later. So in general, fluids flow or involve motion. So what causes the fluid to flow? It may be due to the slightest change of the shear stress and or imbalance in the normal stress. So in this lecture, we only consider the motion without reference to the forces that cause the motion. So this is called as kinematics. Only the basic concepts and terms will be introduced as a basis for analyzing fluid motion without any calculation done on the forces. So by the way, the analysis on the forces that cause the motion will only be discussed in detail in the following chapters. As you guys remember, in lecture 1, I have mentioned about continuum concept, where in the continuum concept, the fluids are considered to be made up of fluid particles that can interact with each other and with their surroundings. So each fluid particle contains numerous molecules. So we can describe the flow of a fluid in terms of the motion of the fluid particles rather than the individual molecules. Okay? So this motion of the fluid particle can be described in terms of the velocity and also acceleration of the fluid particles. So at any given instant in time, a description of any fluid properties such as the density, the pressure, the velocity, and also acceleration may be given as a function of the fluid's location. Okay? So when we talk about location, we are actually talking about its coordinate. Okay? Here we have x, y, and z axis here. And as you can see here, the field representation, the field representation is basically the representation of the fluid parameters as a function of the coordinates. So the field representation of the velocity is given on the slide, where u, v, and w are the x, y, and z components of the velocity vector. Okay. So by definition, the velocity of a particle is the time rate of change of the position vector for all that particle. Okay. And the time derivative of this position gives the velocity of the particle as dr over dt equals to v. Okay. So if you write the velocity for all the particles, so you can obtain the field description as here, where it's a function of position x, y, and z and time. Okay. And since the velocity is a vector quantity, so if you want to get the magnitude of the velocity, you put a modulus and you can calculate. Okay, you can calculate the magnitude. So in general, when you want to analyze the fluid flow, there are two methods or approach that can be used. One is called as Lagrangian, another one is called as Eulerian. So in Lagrangian approach, the movement of the individual fluid particle is followed with respect to time. In other words, you put a tagging. You put a tagging on the fluid particles by putting ink or dye or a marker, okay, and you follow or you track the motion of the fluid particle with respect to time. So this approach is also called as control mass approach. So another one is called as Eulerian. It focuses on certain point in space and describes the motion of fluid particles that pass this point as time goes on. In other words, the fluid properties are written as a function of space and time, and the flow is determined by analyzing the behavior of the functions. So this approach is called as control volume approach, and most of the time we use Eulerian approach. So if you want to see the difference, consider a smoke going up a chimney. So the blue colors are the smoke particle. For Eulerian approach, in Eulerian approach, or by using the Eulerian approach, you attach a thermometer to the top of the chimney at point O. Then the temperature is recorded as a function of time. As different smoke particles pass through point O, the temperature changes and it gives T in terms of position and time. By using Lagrangian approach, thermometer is attached. So this is the thermometer attached to a particle, for example, particle A. So you can get the temperature of particle A with respect to time. Okay. So if you have many particles, then you have to have many thermometers because you have to track each particles. Okay. All right. So next, all right, instead of using velocity to describe the motion of the fluid particle, you can also use acceleration. So by definition, acceleration of a particle is the time rate of change of its velocity. And so if you can see here, the chain rule of differentiation is used to obtain the acceleration. So velocity is described or the rate of change of velocity is described with respect to time and also space. Okay. So this is called as material derivative. The shorthand notation for this long notation is given here with capital D. So if you want to have the material derivative for other parameters, you can fill in the empty space here. All right. So the short form or shorthand notation is given here, where this is called material derivative. This one is the local derivative, and this one is called as convective derivative. All right. So next, so when you analyze the fluid flow, you need to know what type of flow that you are analyzing. Okay. So there are two types of flow. It's steady and unsteady flows. If the flow parameters is not changing with time, the flow field is said to be steady, and if it changes with respect to time, it is called as unsteady flow. So if you can see here, if you plot, if we put a probe right, in the flowing fluid, then you can actually get the velocity, for example. So if you plot the velocity with respect to time, if you get a straight horizontal line, so that means it's a steady flow. Because the rate of change, the velocity with respect to time is zero. Okay, the gradient is zero. But if you can see here, if you plot the velocity versus time graph, if you get a fluctuating line, then that means the flow is said to be unsteady because the rate of change of the velocity with respect to time is not zero. All right. So most of the time, or in most cases, the flow is said to be unsteady. All right. So next is the term that we normally use when you describe the flow pattern. Okay. These two are normally used in experiments, while this one is more on the analysis. Okay. Pathline, Streakline, and Streamline. So pathlines are lines traced out by individual particles of fluid. It can be observed by following the path of a marker as it moves in the fluid. So this is basically Lagrangian approach, where you put a marker or dye or ink on an individual particle. For example, particle A. Now, this one is particle B. So you follow the movement of the particle. So this line of the fluid particle is called as pathline. So if these two lines, pathline through A, pathline through B, coincide or meet, that means the flow is said to be steady. So another term is called as streakline. So streaklines are traced observed when a dye of smoke is continuously injected at a fixed point or points within a flow field. So as you can see here, this path line it stops here, where it meets um, sorry, where there is an obstruction here. eh. So at this point, after this point, you will not get a straight line anymore, right? You will not get a path line anymore. So therefore, this line or trace that you observe here is called as streak line. All right. Okay. So this is streak line. So another one is called as streamline. So streamlines are lines representing the direction of velocity throughout the flow field at any instant in time. Okay. So as you can see here, these streamlines are used when you do the analysis. You cannot see it. It's not. It is not used for experiment, but it is used for analysis. And if you can see here, if the streamlines are closer to each other compared to here, okay, where the gap is bigger, okay, that means when it is closer, the velocity is said to be higher at this point. All right. So if you can see here, if the gap is the same, okay, see the gap is the same, the flow is said to be uniform flow because du over ds, s is the space, equal to 0. But if you can see here, the gap is not the same. Here is closer, here is bigger, here is closer, here is bigger. So this flow is said to be non-uniform because the change in the velocity with respect to space is equal to 0. All right. Okay. So the next term that you need to understand and also remember is the difference between the real and ideal fluid. So for ideal fluid, the fluid is said to be inviscid. Inviscid means no viscosity and incompressible. Incompressible means the density is constant. And the fluid slip at solid boundary. Therefore, velocity exists at the wall. So as you can see here, this is an example of ideal fluid, where the velocity will be the same, whereas in reality it's not. So basically all fluids are real fluid, because in real fluid, no slip condition at the wall, meaning at the wall, you should have a zero velocity, because the fluid molecules tend to stick at the wall. So no tangential velocity at the wall, boundary layer exists near the wall, and the velocity profile developed. That's why you see the difference in the velocity here. The velocity is higher as you go far from the fixed wall. So as you can see here, this is an example of ideal fluid. This is an example of real fluid. Even though we have an obstruction here, the path line goes, or the streamline goes back to its original position here. Whereas in reality, we cannot get this. In reality, there will be disturbance in the flow, and after this, the obstruction, you should get some disturbance here. It is called as zone of separation. All right. So another thing that another term that you need to know here is called as laminar and turbulent. This is the type of flow. Okay. So what is laminar flow? What is turbulent flow? Laminar flow is steady, no mixing, smooth appearance. Flow of fluid with high viscosity like honey and lubrication oil has laminar flow. Turbulent flow is flow with mixing action throughout the flow field with formation of eddies. So basically, um, if you want to see whether the flow is, if you want to know whether the flow is laminar or turbulent, uh, you can see or visualize the flow. Right? If the flow is straight, Okay, there is no disturbance, then most probably it's a laminar lah. Okay, but if the flow is like there no straight line, or you cannot see any pattern, okay, that means it's turbulent. Most probably it's turbulent. Another uh, another technique is by calculating its Reynolds number. The Reynolds number is given by rho u d over mu, or rho v d over mu, where rho is the density, u is the velocity of v, d is the characteristic length. If it's a pipe, normally it's the diameter, okay? And mu is the dynamic viscosity. So when you calculate the Reynolds number, okay, so for practical purpose, the Reynolds number less than 2000, the flow is said to be laminar. So if the Reynolds number more than 4000, the flow is said to be turbulent. So what happened in between? So in between is basically called as transitional, or transition. Okay? Transition from laminar to turbulent. Alright. So for flow in a pipe of diameter d, by using experiment observation, it shows that for a fully developed flow, the critical Reynolds number, okay, is about 2300. So this is for pipe. Note that the critical Reynolds number is different for every geometry. All right. Go back here. This is a Reynolds experiment. I think we also do this in the lab, the fluids mechanics lab, experiment 4. If you see a straight line here, that means it's laminar. If you don't see any pattern here, it's dispersed, that means it's turbulent. And this one is turbulent. But if it's initially laminar, you see a short straight line here, but then you don't have any pattern here, it dispersed, then most probably this is transition, transition flow. But if you want to confirm, you have to calculate the Reynolds number. All right, this one is a flow dimensionality. So basically, when you analyze the fluid motion, you can choose whether you want to do it in one-dimensional flow, two-dimensional flow, or three-dimensional flow. Okay, it depends on on the situation. Okay, of course, if you use the three-dimensional flow analysis, the accuracy might be higher, but then the complexity will be higher as well. Okay, but you can simplify the analysis by using two-dimensional flow or one-dimensional flow. So in one-dimensional flow, the velocity profile is uniform at any station. That means you are using ideal fluid. For that two-dimensional flow, you can use the real fluid, where there is no slip condition, there is velocity profile, the boundary layer. But if you want to have a complex, you want to have a more accurate result, but more complex, then you can do the three-dimensional flow. All right, but it depends on the case as well. So this is the one-dimensional flow, this is two-dimensional flow, and this is the three-dimensional. So last but not least is the frame of reference. So the laws of mechanics are still applicable if the frame of reference is moving. This is normally for sheet. At a constant velocity in straight line, it's easier to analyze steady flow compared to unsteady flow. So sometimes convenient to change the frame of reference from a fixed coordinate to moving coordinates. So this one is more on something that is moving lah, like ship or cart. All right. I think that's all for this lecture. There is no calculation. Later we do the analysis or the calculation in the next lectures. So thank you. You can comment on the videos if you have any questions. All right. Thank you and see you guys again.